is realize digital circuit, which is a NOR logic gate, which you can see in the left side, made by transistors. The circuit will be realized with CD4007, which is one component we are going to talk today in the class. And there are different steps to do this operation. Today we are going in detail to discuss about them. So here now is not important that you will understand actually what's going on. But one part of the lab is kind of like use software, which is called Tinkercad, which is used for drawing circuit on breadboard. This is the result of your drawing in Tinkercad. You can see it's just a kind of an image where you represent the system that you want, the prototype that you want to build on a breadboard with the connection with the different signal generator, power supply, in this case a battery, and an oscilloscope on the top. This is just a representation that will help you in the lab, because if you have done this every time that you do a prototype, then you can just bring this one into the lab and just practically build the system based on this. So you can, let's say like this. Let's say it's kind of like child proof. Let's say like this. So you can also give a child this paper, and in theory, you should just follow this schematic and build it as is shown here. So in theory, your main design issue can be done at home, because you have to just sit on the computer and draw this schematic. And then when you go to the lab, it's just, as I said, is a child proof. So you just go there and build it, even if you are blindfolded. So, and then you just build it, and then you just test it. Can you repeat? Anyone has said something?
Yeah, Lilian tried to say something, but I think they have some echo in the classroom.
Okay. So, okay, then, okay. If you have something to say, just turn on the microphone so I can listen, or write in the chat.
Is this file posted to Cmos?
It will be in after the class, yeah. Immediately after the class, yeah. So, and so my main point is that since this part with Tinkercad does not need to be performed strictly in the lab, I suggest you to register first of all on the software before that the lab start, so you don't waste time in the lab. And if you can, I suggest to start actually to look about this part, or to start this one by your own before that the lab start. This because in this way you can just go to the lab just to build the circuit, and go directly to the lab by doing this, by having this paper with the schematic done. However, again, if you find, this is my recommendation, if you find any issue in drawing this, you can stop, and then you can come, and then you can ask what are your issue in drawing the circuit. That's not a big deal. So you can continue in the lab. But my personal suggestion is try to, if you can, finish this drawing on your own. And since the lab will be tomorrow, then maybe spend a little time this afternoon and try to understand how to work how it works. This software is very easy. I mean, it's not difficult. I think you have used much more difficult software. Even when you play a game, I think is even more complicated than this software here. So, and you can see also from the picture, it's very childish. So I think it should be quite straightforward for everyone to understand. But again, it depends if you have some. If you have maybe worked before with some software like this, maybe then you can go faster. But again, it's still possible that someone has some issue on drawing this circuit, especially when you want to bend wire. Maybe it's not straightforward. I try to document all the steps, so try to follow it. I also try to make a video. The paper, the document Word file will be available immediately, maybe after the class. But the video, as you say, I need a little time to upload it in the system, and because it's very big, so it might take a little time. Okay, so again, so when you will come to the lab, then you will do the second part. So this lab will be divided into part. Part A, which is the part of Tinkercad, and part B, instead you come to just build the system. And in the part B, at the end of each part, there are some questions. For example, here, I ask you to change the color for the wires. I ask you to replace the battery here with the power supply. I ask you to take a screenshot then of the system and then paste it on the Word file, which is the answer of the lab. So I'm not asking you to build a new system. I think the important is just you see what is the procedure, and then you can also take some of your time to look into it. Also because we have finite time and limited time, so I cannot ask you too much. In the second part, then there will be all the instruction about what to do in the lab. I will try to add some pictures. I actually can upload the first part immediately, as I said before, after the lecture, but the second part I went to the lab before and I took some pictures. So as soon as I upload the picture, then I paste it here and then it's done. So here there are all the instructions for what you have to do in the lab. Again, if I have time, I will do also a video today about this part here, but I know that the lab is tomorrow, so I'm not sure. But anyway, for tomorrow, I will be there. So then at least we can also see face to face for the first time, and that would be, I think, great. So I can also try to be a little more familiar with your names, because in the list it looked like more like a supermarket list. So I don't actually cannot be so. And also sometimes I get familiar with the students when I see your face, and then I remember you in this way. So if for you, all of you that you are here in the class is okay, perform a lab as I said, then that would be great. If for someone of you is not okay, or you have some question about it, then ask now if you can, or send me an email as soon as possible, because I need to know if the lab actually is okay or not. So you cannot send it to me tonight, because then I cannot go at 11 p.m. to the lab and look about and change the things. So please send me an email maybe before 4 p.m. of today, and then I will look at them and I will evaluate what is the feedback, and I will give you official message on Canvas about the time for tomorrow for the lab, which you already know, but I will just send a message to confirm that the lab will be there. I mean, the lab will be there because I don't move the lab, but the lab will take place. Okay, so if any one of you have a question about it, then talk now or don't do it anymore. But yeah.
Luca, the pictures you showed us,
Yes.
these are just a reference, right? When we're connecting the circuits and everything, we just look at them and
Yes,
use them as a reference.
yes, that's correct. So if you see,
we're not actually going to use an application on a PC to build this.
no, I
That's
mean,
what I
you
mean.
don't have to use this picture here. You don't have to use this picture here that is in the document, which in the end actually, okay, you have to use the software in your PC to work with the software Tinkercad and produce the same picture that I've shown here.
Okay. So
Yes.
so just to confirm, we're going to use a software on PC.
Correct. But
okay, we're not going to work with our hands.
You also will do that, but that one will be the part 2 of this lab. So
okay, the part where we test things with the oscilloscope and
correct. Okay. So in the first part, we are going to you're going to just use the software to draw this picture here, and then after that the second part is mainly in the lab, where you connect the system as you draw it here in the document.
Okay.
Yeah.
Ula said we have to do part 1 at home.
Yes, the part 1 is suggested to do it at home, but if you are not able to do it, then you can continue in the laboratory and ask me the question about the software that you were not able to do. So I recommend to start at home. If you can
Yeah,
finish,
but
that
how
would
do
be
we
great.
download the software, and is it free online, or
Yeah,
do we
that's
need a
good.
license?
Yeah, that's indeed my fault. And I will show you now.
Did you put it in instructions, Luca? I saw
Yeah,
it
actually,
on
it's
the
everything
page.
written here in the sense that the software is free. The software is online. You don't have to download anything. You have to just register. That's
Okay.
why I also like this software, because you don't have to fill
Okay.
up your computer with a bunch of useless software. Yeah.
So everything is written in that file.
Correct. Again, I said, of course, maybe someone of you could say, okay, they say useless, then why we are using, right? So the point is that for you that you're learning, this one is definitely a good help and a good support for starting to understand how the system works and how to build the system. However, of course, as soon as you become more experienced, you maybe don't need anymore to draw this one in Tinkercad. Although, again, for me, at least now, for example, I don't use it much. But when the system becomes very, very complicated, then it's very big help, this software here. So, for example, for this system that I'm suggesting you to build here, in theory, there is no need for Tinkercad. But of course, I cannot ask you to build a computer here because it's the first time that you go to the lab. So, so in this case, using the software is a little overkill for this lab here, but you have to learn. So the first time that you see it, so I think in this case will be also useful for you. Okay, but said that, I think I've said enough about this. So again, the software is free, so you keep your cash, and the registration is the only thing that you have to go through, and then you can work online. The same also with EasyEda, which will be the software that we will do in the third lab. LTSpice is also free, and you can download whenever you want, but you have to work with that offline. But EasyEda and Tinkercad, you have to work online. Okay, I just noticed that I'm wasting a lot of time about these details, but I think it's very important. Okay, so I think for the lab I said everything. Nothing else to say, I suppose. Yeah, okay. I want to say something. Okay, yes. I was remembering it because I have some notes about what I have to say because my memory is very bad. So communication lectures. Okay, rule the lab I said, laboratory 1 I said. Okay, yeah, another things, then it's better to, anyway, today we have a lot of time. Let me go to Canvas. Then I share my screen. Okay, I hope you can see my Canvas now. Great. And I've updated a few parts of the website. So I'm going here in the electronic Delen part, and here there is one new section in the bottom, which is called the rules for MIE 3801. Here I have explicited better what are the requirements for this part of the course. You have 6 oblique, you have 7 labs, which means 1 less than MIE 2000N, and you have only this one here, the labs. So I have selected for you which labs you have to follow. For MIE 3901, you have to do this one here called electronic instrumentation, which instead is not mandatory for MIE 2001. This is because some of these 3901, some of you has come from master courses, or at least you don't have a very good recall of this concept. So I need to check that you know these things very well. And it happened many times that the students of 3901, you definitely have a big luck on this concept, but maybe this year won't be the case. We will see. But MIE 2001 should not do this lab. Should start directly from Cmos digital circuit, which is the one that will be tomorrow. If you are me 3901, you have to just contact me, because this lab, we have to set a date and time for this lab here, for the lab 0. Okay, and here in Forelesning Notater 2020, you can see there is the PDF and there is the link for the video. I have created a YouTube channel where I can earn money. No, I'm kidding, but I can. You have all the video for this course, and about the Forelesning that we had yesterday, and one part of the Forelesning that we have. One part of the Forelesning that we had Thursday, and the full lecture of the full first lecture. Okay. And okay, so then you can just go in YouTube and then see the video and so on. So if you wish, you can look about this video, which are not many real time, so they are not the actual lecture that I'm doing. So they are actually extra video, which contain the same contents of the lecture, but and it's possible also even more. So if you have time, look into it, but more or less is the same content. So maybe 1 or 2 information will be given more. Okay, so I think this was the last thing I have to communicate. Let me see. Okay. Another thing is that I need that you prepare the groups for tomorrow. So send me an email, or send me an email with the name of your groups, and so I can then add the groups here. I'm actually not sure if you can actually do it by your own, but here, for example, for me, can you see my canvas, right? Okay.
Yeah, we can see it.
Yeah, we do.
But when it comes to groups, how like, because are we supposed to choose our own, or are we gonna get?
Yes, you decide by your own. You are free to decide your best friend for your project, and then you just work with in this way for all the labs. Yeah.
And Luca.
Yeah.
A question from Lillian. Like, is the max persons about the group is at 2?
So yeah, correct.
Yeah,
Not
2.
more.
Okay.
Yeah.
Only 2, Lillian.
Sorry,
was that the wrong question? Oh, project. Yeah, it's like, yeah. So for the project also, it's for 2 persons.
Yes, correct.
Yeah. So lab and project 2 persons. Okay, thank you.
Correct. So if you can access to this area, then you are free to do the group by your own, but probably I can only view these things because I'm the lecturer. So then you have to send me a list of these groups. And then I will
we see also the group on the persons. Yeah.
Okay. So I think maybe you can already, you just have to kind of like drag and drop, and then that would be done.
Yeah.
Yes. So yeah, for the groups will be the same. I mean, you can decide to change group for the project again. You are free. I give you the freedom to do that, but usually it remain the same. Again, it's up to you. I don't like to force you to do what you don't want. So just feel free to do whatever you want. But the important is that the group is made by 2 persons. Yes. So okay, I think this is all. So I need to have the group hopefully before 4 p.m. So please send me the list or send me your names before that time. Great. So I think that was all. Yes. Okay. Anyway, I have to start with Forelesning because otherwise here we just talk about bureaucratic stuff and we don't start. Okay, hopefully we are, you can see my screen with the slide, and we are going back to what we were talking last time. So finally, you have seen how to build, let me think. an inverter with the transistor. I hope we arrive until that point. Done many things. Okay. Slide 106, I suppose. I suppose we were arrived here. Can you confirm? My memory is very, very bad. So if any one of you remember or wasn't sleeping the last night.
Wasn't we finished with this and started on point 4, I think. I think you finished this.
Great, great, great. So I
Yep.
will just briefly summarize a few things about these things. Okay, so what I've said last time is that digital logic circuit are made by transistors. And this is the slide which summarizes the operation of NMOS and PMOS, which are two type of MOSFET, which is again one specific type of transistor. We need two type of transistor, we need two type of MOSFET because we need two type of switches, as I showed last time. Otherwise, we cannot build inverter. These two switches work in complementary way, which means that they work in opposite manner, opposite way. So it means that when you apply to the gate voltage of the NMOS VDD, then the NMOS will work as a closed switch between drain and source. So the current can flow from drain to source. If you have that the gate voltage of the NMOS is 0 volt, then the MOSFET work as an open switch, which means that the current cannot flow from drain to source. The opposite happened for the PMOS. If the gate voltage of the PMOS is VDD, then the current cannot flow from source to drain because the MOSFET behave like an open switch. And let me do the pointer things, okay? And if the gate voltage of the PMOS is 0 volt, then the PMOS work as a short circuit or closed switch, and therefore current can flow from source to drain. So I hope that this part was at least clear. And every digital circuit that is made of PMOS and NMOS is called complementary circuit because PMOS and NMOS are complementary. And therefore, these circuits are called Cmos circuit, where the C means complementary. Here, I've shown again that PMOS and NMOS work as, we have to think in digital circuit that PMOS and NMOS work as switches, okay? So this is what happened in these two different cases. Okay, so now we're going to use these little concepts for designing something a little more complicated than not logic gate. With this one was a little trivial, let's say, or easy. So last year I've taught one method, which is let's call advanced method for designing CMOS digital circuit, and is usually very common in designing. But again, I see that this one may be a little complicated. So this year, just for making it a little more feasible, the course, and going a little toward your request, at least your previous colleagues, I propose a new method, which is much simpler and is based on logic gates. But this is required that you know logic gates, what are logic gates, and especially NOR, NAND, and NOT. Why this? Because as I hope Jorgen already explained, every digital circuit, any digital circuit, can be just made by using or only NOR or only NAND, right? I think, I hope he said, but if he didn't said, then I said it to you now. So any digital circuit, you can build it by just using only NAND logic gate or only NOR logic gate or only NAND logic gate. Yeah, okay. So the method I'm proposing you requires something that I don't like, but I think is maybe easier for you, which is remembering these three circuits. The left one is the one that we proved last time, which is the inverter logic gate, not logic gate, with two transistors, PMOS on top, NMOS on the bottom. You have to remember the NOR transistor implementation with our 4 transistors, 2 PMOS and 2 NMOS, and also the implementation for the NAND. Also here there are 4 transistors. The difference between NOR and NAND is that in the NOR we have 2 series PMOS and 2 parallel NMOS. In the NAND we have 2 parallel PMOS and 2 series NMOS. If you know this, then you can design any digital circuit. So please try to remember. Although again, I don't like it, but it will remain impressed in your mind if you do training. Yeah. Okay, I don't want to prove you because for lack of time and whatever, because otherwise I have to explain you the other complex method. I don't want to prove you, I cannot prove you, although I want, how this circuit come out, okay? But I want that you understand how does it work. So at least you have kind of like an understanding why this has to be like that. So what we are going to do is something that is also required probably in the oblig that you will have for this topic. So pay attention, because if you understand it now, then the oblig will be much faster and easy. So the first step to understand how a more complicated digital circuit than not the logic gate work is to start with the truth table, which is the one in the left. Here you have the 3 column because we have 2 input and 1 output. A and B are the input and output is the output. Yeah. In this case, you know that the system to be characterized need to be characterized by using the different combinations. So 0, 0, 0, 1, 1, 0, and 1, 1. And for each combination, you have to calculate the output, right? This one defines the behavior of this logic gate. I think you remember the behavior of the NOR logic gate, which is described anywhere here. But let's try to understand why it's like that from electrical point of view. So let's start from the first combination. So we are assuming that I can use the pen here, so we can do it together. Yeah. So let's assume that input A is 0 volt and input B is 0 volt, which means 0, 0, as you know. And the output is 1 in this case, which means VDD. This one you already know. So I write here 0 volt because A is 0 volt and B 0 volt. Also here, the gate of the Cmos is 0 volt and here is 0 volt. Okay. So based on what we studied last time, if the PMOS has the gate voltage of 0 volt, then this means that the PMOS is on. If the PMOS also MP1 has the gate voltage of 0 volt, then this means that the PMOS is on. Again, on means it's a short circuit. So there is a connection between source and drain. There is a connection between source and drain like this. If the NMOS has the gate voltage of 0 volt, then the NMOS is off. So Mn1 and Mn2 are off. So I cross them. So they are equal to open circuit. So the question is, what is the voltage in this moment at the output terminal? Well, it's easy because you have that the PMOS MP1, MP2 connect the output terminal directly to the positive power supply. So it means that the electric potential at the output is equal to the electric potential at the power supply. And here we know that the electric potential is VDD. So the output is just VDD. Okay. So sorry if it's ugly my way to write, but I tried to draw with the mouse. Okay, so I hope it was clear, and you can repeat this procedure for also the other situations. Let me see if I did it on the video, if I did it in the next slide. So I hope this one is correct. So again, we prove that the output is VDD because again, from the truth of table that I showed you before, the output should have been 1. And as I say here, the output should be VDD. Okay, let me, why this one doesn't change? Okay, so this is just a summary about what I said before. I wanted to do it with you so you can follow me better, but here this is just a summary of what I said. Again, here I wrote that you should be able, if you understood this procedure, you should be able to perform the same procedure for the other combinations. If just for you, I will try to do another combination, just at least we have a little more training together. So let's consider the combination number 2. I put the arrow now, which is 0 volt for A and VDD is B, and the output is has to be 0 volt. So we have to prove that the output is 0 volt. So I write here 0 volt for A, VDD for the input B. Here is, I have to remove it here, here is VDD at the gate of this MOSFET, and then here is 0 volt. So again, if the PMOS MP2 has gate voltage 0 volt, this means that the PMOS is on. So it means it works as a short circuit. If MP1 has the gate voltage of VDD, this means that is an open circuit. So it means that is off. Okay, cross. And if the NMOS MN1 has VDD at the gate, this means that the MN1 is on. So this is a short circuit. If there is 0 volt to MN2 at the gate of MN2, this means that this one is an open circuit and is off. So off, and then here I cross it like this. Now, what is the voltage at the output terminal? Maybe any one of you can try to answer. Microphone.
Should be 0.
Great, because we have that the
Short-term
MN1,
0.
yeah, connect to the ground terminal, which I told you last time is nice to think that is at 0 volt. So the output terminal is connected to the ground through MN1. So there is a connection here. So the electric potential at the output is equal to the electric potential at the ground, which means that here is 0 volt. Okay, so I think you have understood how to proceed, and I think with a little training you can become a pro in these things. Yeah. Okay, so let's proceed to the next thing. Okay, now something a little more challenging. So I'm going to add more and more difficulties and maybe make it more difficult. So if anyone you have a question, please stop me. We want to design an AND logic gate, okay? And with a MOSFET. How do we do that? Again, I never show you how to implement AND logic gate, but with the few information that I give you, you should be able to do that. Let's start by thinking about the Boolean formulas of the AND logic gate, which is this one here. I hope that every one of you remember. If you don't remember, just look into the digital technique book. Okay, so an AND logic gate can be actually realized by using, as I told you before, NAND or NOR. Because if you use NAND or NOR, you can realize any digital circuit. So now it's just up to you to decide if it's better to use a NAND or a NOR. Okay. How do I decide? Well, in this case, it's easy because NAND sound like AND. So it makes sense to use the NAND, you understand? So in this case, there is no problem. So in this case, we are going to use a NAND. But how can we use a NAND for realizing an AND? So let's have a look about the NAND Boolean formula, and let's compare it with the AND Boolean formula. So what is the difference? It's just an inversion. And if I invert again the output of the NAND, these two inversions cancel each other, and then you get an AND. So the trick here is just to use a NAND and then use an inverter to negate again the NAND. In that case, you get the AND formula. So I'm just maybe writing here, maybe Y. This is the NAND. If I invert the NAND once more, this one cancel with this one, and the result is AND. Is the AND between A and B. So you understand that what I can do is just draw an AND with the input A and B. It's very, very ugly, but okay. And then you can add an inverter after. And this is your AND. So all of these things work like a big AND logic gate. Okay, I hope it's clear. And here what is this mess? Let's remove these things. Okay, I like to go show the procedure with you, but then I have to remove it. Yeah, there. So now, as I told you before, I told you to remember what is the MOSFET implementation of an NAND. So you just have to replace the NAND with the MOSFET implementation. Okay. So here, so this NAND here, you have to replace it with this circuit here, which I showed before. Let me go backward, which is one of these three that I showed you before to remember, which is this one here in this case. So, and in this case, we put it here. So we replace this NAND here. And then we do the same for the NOT. So we replace the NOT with the MOSFET implementation. So this one is the implementation MOSFET of an AND logic gate. I think it's pretty straightforward once you have the logic gate circuit. So this is the method that I want that you use this year for realizing any digital circuit. If you look about the Forelesning notator of last year, it's much more complicated because that is actually the one I explained last year is the best method you can use. This one is a method, but is not the optimal method that you can use, because the other method you can actually minimize the number of transistors, which is important when you do real design. But in your case, you are learning and you want something just that it work and it make what it should do. But when you go to company, then the other method maybe would be useful. But again, it's something that I think I don't have time in this course to do it. There should be another course called Digital Electronic Circuit where I should go in detail then in that, because there are many other techniques that are even better than the one I explained last year. So, but again, for the moment, I hope you are happy with this method. Yeah. Okay, so another things, example 3. Design a NOR or an AND with n inputs, where n means 1 or 2 or 3 or 4, whatever. So as I showed before, if you consider just MP1, MP2, MN1, and MN2 on the left side for the NAND, then you get 2-input NAND. So this is a 2-input NAND. And if you want an n-input NAND, you have to just add PMOS in parallel and NMOS in series, depend on how many input you have, of course. If you have 4 input, then you need 4 PMOS in parallel and 4 NMOS in series. And that then you get your 4 NAND input, or 4 NAND logic gate. It should be pretty straightforward. The same things is also for the NOR logic gate. Okay, I don't, in this case, if you want more input, you have to add more PMOS in series and more NMOS in parallel. Okay. Okay, you will have one exercise of the Bligo in this. I don't go through now because I think it's pretty straightforward, but if you have any questions, just feel free to ask. Example, what should be 4? Yes, but I wrote it 1. Is okay, I suppose. 4 there. Okay. Now, we are going to more difficult exercise before the break. Here, you have to design a circuit which has these Boolean formulas here. And the first step here is to transform these Boolean formulas in logic gate. I think this one you should have done in digital technique. I definitely hope for you. And if you know how to do this, then you can also understand what I have done here. And to make it even clearer, then we are going through together. So in this point here, I have A inverted because the A got the input to the NOT and then is inverted. Then we have in the other input, we have here B, and then the output of the AND is A inverted B. In the bottom side, we have B inverted and we have A. And the output of the AND here is A A, B inverted. The OR do the sum, right? So the result is A inverted B plus A, B inverted.
It's like another or something like that.
Correct. So I mean, the OR logic gate, remember, maybe, can write it here, maybe. OR is equal to plus, and N is the equal to the product, okay? Times, I don't know, X times, I don't know, yeah. So whenever you see a product on the Boolean formula, you have to think about AND. Whenever you see a sum in the Boolean formulas, then you have to think about OR. So this one will be an OR, and here in between there will be an AND. Okay, so this will be an OR, and here it will be an AND. Okay, then it's very straightforward again. What is the next step? Is just replace each logic gate with the MOSFET implementation. So this is the MOSFET implementation of this circuit. So just for you, this is the NOT. This is a NOR, and I told you that NOR followed by a NOT become a NOR. Sorry, become an OR here. So here I draw a NOR followed by a NOT, become a OR. Then you have here, you have an AND, and you have also a NOT here logic gate. So this one become an AND, and here you have super ugly. Okay, and here is a NOT, and here is you get the AND. This is a very ugly picture. Okay, and this is simply a NOT, and also this one is a NOT. So if you compare this circuit then with the previous one, then you will see it's the same. I just replaced the gate. Okay. You see that as soon as the circuit starts to be complicated, also the MOSFET implementation becomes even more complicated. So again, some of you may argue, why should I do this drawing? I have already the other one. There is no, I mean, I know that I have to replace it. The point is that, first of all, if you draw this circuit, you get more familiar about what are the MOSFET implementation of NAND, NOR, and NOT. And second is that there is some tricky things here, because if you will try to repeat by your own this exercise, and I suggest to do that, you will see that you will have some kind of like difficulty, because here I try to connect all the wire together, while instead the logic gate, for example here, this one and this one, you usually see like input. You don't have a connection with other logic gates. So, okay, my suggestion is just try to do it together alone, and you will see that it's not as simple as you think. Okay, and try to understand and try to train and try to obtain the same figure. Yeah. Okay, so yeah, and also it's very important because this is a first course of the electronics. I will also mention this when we start the Elektrische Kretzer review, let's say like that. But this kind of electronic we are doing is called electronic with discrete components. There is another electronic called ASIC design, which means integrated circuit design, where you just work with MOSFETs. And there you definitely need this schematic. So it's better you learn it now than you have more things later to learn. Okay, so but we can take a break, maybe 7 minutes, 10 minutes, yeah. As you wish, so 10 minutes, yeah. So at 1:15 we start again.
Okay.
Let me share the screen. Wait me 1 second. one student here. Ask one fast question. Okay. Here we are. Let's see. Yes, so the previous admit, okay. So the previous exercise were design exercise. So design electronic circuit by using MOSFET. Another type of exercise that you can find in Oblique is the analysis exercise, which we are going now through. So it's very important that you understand how to read one circuit with MOSFET, because it happened in company that maybe in your future work, hopefully that someone will I don't know, go to retire, or you will continue the job of someone else for some reason, and it can give you maybe a paper with this schematic with the MOSFET, and you have to know actually how it works, because you should not always trust that the circuit work, and then it means you need to be able to read the schematic. So this is very important. We are going through this exercise. It starts to be maybe complicated, but you will see it's not that difficult. So in this particular exercise, I'm asking you to find what is the waveform Q given the input D0, D1, and select. So in this circuit, you have 4 transistors, 4 MOSFET. You have 3 input. One is called D0, one is called D1, and one is called select, and one is the output Q. Okay, so someone is applying a signal in D0 and D1 and select, and the signal is the same that is plotted in the right side of this slide. Is this one here? And you want to know actually before to turn on the circuit, what will be the waveform at Q that you expect. Okay. So to do this, I think, yeah, I think this one I have to do it here. Yeah. So let's do it this one together. And to do this one, I have to start from the plot and divide the plot in intervals whenever there is a change in input. So you can see now I draw the line because in that moment, select change. So I call this one T1 and this one 0. So now I want to understand what happened to the circuit in the time interval between 0 and T1. So what I do is check that between 0 and T1, you have that D0 is equal 0. So I wrote here 0 volt. D1 is equal 1. So it means it's VDD. And select is equal 0. This means that is 0 volt. Now it becomes practically the same exercise we have done before for the NOR and the NOT logic gate. We have to understand what is the state of the transistor. So if the transistor is off or on. So let's start from the bottom transistor, this one here. The gate voltage is 0 volt. So this means that the MOSFET NMOS is off. This one is off. Then this 0 volt go through an inverter, so become VDD. So here I write VDD, just to remember. So this VDD is applied to this Cmos here, and this Cmos is what is the here, and this VDD is off too. This MOSFET is off too. So remember, when the gate voltage is VDD, the PMOS is off. On the other side, instead, in the top PMOS transistor, you have that the transistor is on because the gate voltage is 0 volt, and the missing NMOS here as the gate voltage of VDD, which means that also this NMOS here is on. So what is the value of the output? Well, the output, I can just draw here, this is a short circuit, this is a short circuit because they are on. So the output is connected through these two top transistors to the input D0. So it means that the output Q is equal to D0. And D0 this time is 0 volt. So it means that Q is 0 volt. So I'm going to draw in the plot 0, like this. And then I have to repeat this procedure for all the other situation. So what I will do now is divide the plotting in time intervals whenever the input change. So I'm just doing now once for all.
So this is this will be triggered when some change on some of the inputs is
Correct.
changed. Then.
Hmm.
Okay, so it's not always on the select part. So it's only it should be on every change in this circuit then.
Correct. Correct.
Okay. Okay.
Correct. And I will let you try to make you think actually what the device is. It's something that you have seen already in Digital Technique, I hope, but we will see later. Maybe when you see the MOSFET implementation, you cannot understand, but later on, I will make you think about, try make you to remember what it is. Okay, so let's analyze now between T1 and T2. Between T1 and T2, D0 is equal 0, so I write here 0 volt. I'm going a little faster now, so. One thing that I maybe forgot to say before to start this case is this one. That may be confused a little. You can see in the circuit here, there is some dot, some black dot, where it crosses kind of like some wire, but here there is no dot. So what does this mean? It just means that this wire here
Goes over the other one, isn't it?
Correct. This one are electrically connected together,
Yeah.
but here there is no electrical connection. So it's just because the drawing cannot be done in other way. I mean, it can be done in other way, but I can show you maybe how can it be drawn.
Yeah, we had that in electrical cluster now in this autumn. So yeah.
So you know, okay. It could be drawn like this, but again, I hope you understand what is the meaning of the dot. So every time you have an electrical connection between wires or wires, always draw the dot. It's much better, make more clear the schematic. Okay, so let's go back. So between T1 and T2, the input D0 is 0 volts, so I write here 0 volt. The input D1 is VDD, so I write here VDD. The select is VDD. So I'm going now a little more faster, so I hope you follow. So this MOSFET here is on, so this is short circuit. This MOSFET here is on, this is short circuit. This MOSFET here is off, and this MOSFET here is off. So this means that we have a connection between Q and VDD this time, or D1. So here in the plot, I draw 1 or VDD. I repeat again, this one for the next situation. I'm just doing, I know it's boring, but I know that I just do it for you so you can train. And yeah, so in this other situation between T2 and T3, we have here, I can also write 1, it doesn't really matter, 1, and here 1, and select is 1. So the NMOS is it wrong? Is on. So this NMOS here is on. Remember, 1 means VDD. This one is on. This one is off, and this one is off. So in this situation here, we have still a connection between Q and VDD. And here we do like this. If I go too fast, just stop me and tell me that I'm going too fast. Interval T3, T4. D0 is a 1 for VDD. I just use both so you can get trained. Anyway, they are the same. And this is VDD. Okay, so the NMOS is on.
Oh, hi. Sorry, I was speaking with my microphone muted. I had to miss the first half of the lecture. So could you go back to, sorry, now my settings are getting, okay. Why when D0 was 1, why was the C1 not connected? Could you explain that to me? I'm sorry if I'm having
no problem. I will try to maybe repeat it again with all the details. Anyway, it's good for everyone to see.
Thank you.
So let's consider, let's go through, for example, the case of T3, T4. So I will then provide all the details in this case. So in this case here, between T3 and T4, we have that the select is one VDD. So we have VDD applied to this NMOS here. And if you have a gate voltage VDD applies to NMOS, then it means it's on. So it works as a short circuit. This VDD here go up, 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 and apply to this PMOS here on the top. And this PMOS here has a gate voltage of VDD. So this means that this is off because the PMOS work in the opposite way of the NMOS.
Oh, okay. Yeah, that's what I missed out on.
Okay.
But how aren't they the same since there was like the little ball on top of both of them, or am I?
The operation of PMOS and NMOS are opposite, and the symbol of PMOS is that one with a circle, a ball on the gate. The symbol of the NMOS is the one without.
Okay.
So you can discriminate or differentiate these two devices in this way.
Yeah, okay, so you're just like making the current go through it and like, okay, it's going to reach the ball thingy first before it actually reaches the thing without the ball thingy. So that's why it's off, right?
The reason it's off is just because I can go a little backward, so it's even more clear, hopefully. Let me see. We just discussed, hey, what happened? Here, okay. We discussed last lecture that the PMOS and NMOS works as a switches. So then, as you can see, okay,
it's
now
okay.
okay, but
you don't have
I
to.
think you understood that they work in different way. If you look about this table,
Yeah.
you can understand that when one is on, the other one should be off.
Yeah, yeah.
With the same gate voltage, yeah. Great.
Yeah, I do. I was just a bit confused there for a little bit since I missed a little bit of the lecture, but yeah,
Yes,
I get
yes.
it.
Yeah, it's very welcome this question. So that's a good question.
Thank you.
Okay, so let's proceed. If anyone has again any question, feel free to ask, because again, I definitely insist to the fact that this lecture is for you to learn things and not to look at home on your own. So you come here for one reason, so to learn, and I'm here to answer. Okay, so here I forgot how much was, okay, let me see. So the 0 was 1. The 1 is 0. Select is 1. I'm considering between T3 and T4. So this means that this one is on, this one is on, this one is off, and this one is off. So this means that we have a connection with D1, which is 0 now. So here we draw 0. So the Q is connected to the input D1 through these two bottom PMOS. Yes. Then we are going to the next situation. So after T4, we have that D0 is equal 1, D1 is equal 0, and select is equal 0. Again, I on purpose use sometimes VDD and sometimes 0 and 1 because they are the same. I want that you train in this, in thinking in this way. So this MOSFET here is off. This MOSFET, yes.
Jeg spør om noe. Vent da, jeg kan skru på kamera her, kan jeg ikke det? Fordi, ser du nå? Nei, jeg vet ikke. Ja, ok, bra. For vi lurte på ting. Wouldn't the output be the same if you remove the part of the circuit, after the inverter, inverter out, not gate?
Okay, like, so okay.
Wouldn't this be the same?
That's correct. Is correct. Yes, yes, and that is a good good observation, and there is a reason, of course, of it, and unfortunately, you cannot understand it at this moment because we need some concept of analog electronic to explain actually this reason. These two MOSFET here in parallel together, they're called transmission gate. So it's a particular type of switch which has one particular purpose. And if you build the circuit as you did, there will be an issue. And you will anyway experience in this course, and I will show you what issue it is, but not now because you don't have sufficient knowledge. Yeah. Great. Okay, so then that's a very good question. Yes, we will see later on. I would like to say now, but then I spoil too much. But okay, let's continue. So after T4, we have D0, which is 1. D1 is 0, select is 0. So this means this is off, this is off, this is on, this is on. And then we have a connection between Q and D0, which means that the output here is 1. Yeah. So anyway, I also did on purpose in some way fast, because you have to be fast like this. I mean, I'm not fast in doing this because my experience, because as I say before, I'm working in analog electronics, so I'm not working every day with digital circuit MOSFET. But again, if you understood how PMOS and NMOS work, you should be fast. So yeah, that's correct. Of course, this doesn't mean that, I mean, try to give a reasonable answer too. Yeah. Okay, let's see. Next exercise, this one here. This one is kind of more complicated. Okay, I said something before, I didn't say. So based on what some of you already discussed and said, that this select input is actually more important than the other two, than D0 and D1. So you can think that D0 and D1 are actually the input of the device, but select is still an input, but it's kind of a control input, which means that control the behavior of the circuit, okay? In fact, if you notice, if select is 0, then the output take the value of the one input, for example, D1. If select is the other value, then the output take the value on the other input. This is a behavior actually that you should have already seen in a device that is explained digital technique. And actually would be great if some of you can add some guess.
Isn't it a MUX?
This is a multiplexer, correct?
Yeah. Mm-hmm.
This is a multiplexer. So this is how to implement multiplexer with MOSFET. Again, I cannot explain in detail why we have PMOS and NMOS. It's something actually you will learn, because you have to use this technique in your project. If you don't, your project will not work. So you will anyway understand it later on. But keep it in mind. Okay, so we are going to the next circuit, which is also a very known circuit. Maybe from the name, from the name of the inputs, maybe some of you can guess. We have a D input, we have CK, but again, CK is not the correct name here. I will explain you later on. And then we have the output. Okay, let's dig into it, and then maybe after the behavior, you can understand actually which kind of, after we solve the exercise, you can understand maybe what kind of component it is. Okay, this time I have to already anticipate that this device as an extra, can do an extra operation, which is storing data. So this one, it means that this circuit, okay, I just spoiled it. So it is kind of a memory, okay? For this reason, it's important to know what is the value of the output in the past. So before the moment where you analyze, okay? So this is why I put the value of the waveform now also before 0. It's very important, okay? Before the 0 time. Okay, so let's go to, okay, I have a question in the chat. Let me see. Yeah, is it a latch? Is it a latch D? I hope that you have seen it actually in digital technique. If you don't, then it's a very big luck or miss or whatever, because it's one of the most important components in this project that you will do.
No, it's from the digital thing, so I remember it only.
Okay, great, great. Okay, so anyway, as we did in the previous exercise, we are going to divide the plot in different intervals. So I try to do very fast, although fast is not. But... Okay, so I call this one T1, this one I call it T2, T3, and T4, and T5. There. Okay, let's have a look what happened in between 0 and T1. D is equal 0, so I write here 0. CK is equal 1. Let's also write VDD. And let's write also 0 volt, just for remembering it's the same things. And we want to understand what is the output. This is the situation. What I draw here is the situation before 0, okay? So in this part here. And the output is 0, okay? Now, between 0 and T1, the situation remained the same, so it makes sense that the output remained the same, okay? So I draw 0. But then at T1, CK change. So what will happen when CK change to 0? So I change here the value of C0 of the CK, 0 volt. In this moment, what happened is that this NMOS is off. This PMOS is on. And what will happen to these two inverter? This is a good question. Because if you see about it, if the NMOS close to the D input is off, then the circuit has no input. Is it correct? So this D here cannot go through because the NMOS is off. So what is the input of this inverter here? The input of this inverter here is actually the output of the system. If you see about it, if you see very well, this point here is connected to this point here through the PMOS. So you can see that the output of this circuit in this situation, which is 0, become the input of this inverter here, which is 0 volt here. And here in the middle, there will be VDD. So this inverter here force the output to be VDD. And this VDD here force the output of this inverter here to be 0. So practically, in this situation, the circuit does not change. So store the data in the circuit. Okay? So here is 0. Now there is an interesting situation that will make you understand better what's going on. Because at T2, D change. D become 1, right? But again, the NMOS connected to the D is off. So the output does not feel anything, does not feel any change. This means that the output continues to be 0. You understand? Because this circuit is kind of like storing the 0, is memorizing the 0. At T3, what happened? We have that CK become 1. So in this situation, what will happen? So I change here CK, VDD for 1. And I cancel this one and this one. So I cancel here, here. So CK become 1. I'm between T3 and T4. So now this NMOS is connected like this, and now this PMOS is off. So now what happened is that the D input can indeed, I forgot to change also the D, because the D is 1 now. There it is. Okay, so the D now can go through this inverter, and then the other inverter, and then finally modify the output. So the output of the first inverter is 0, and the output of the second inverter become now VDD. So the value will pass from 0 to VDD. And so here, between T3 and T4, become VDD. After T4, so I have to remove here. After the input remain VDD, the D remain VDD here. After T4, between T4 and T5, we have that CK becomes 0 again. So this one becomes 0. So this one is off, and this one is on. So now the output is VDD, okay? And the output become the input of the first inverter. And because the D now is disconnected, the D doesn't really affect the output. Therefore, the output remain VDD. And now the D after T5, the D change, but it doesn't really matter because the CK doesn't change. So the input NMOS remains still off. So then the output remain 1. I know this circuit is kind of more complicated than the previous one because it has memory and you have to try to understand what I've done here. But if you have a question, please feel free to ask. I'm sure that there must be some doubt. It cannot be as so easy. Otherwise, I think this year you have. I mean, otherwise it means someone of you already have worked in this field. I think, which it is possible, but this one should be something difficult. Any one of you has some question? No?
It's a lot of questions, but it sounds reasonable because for me, just remember it from digital technique last year, but yeah.
Okay, so but okay, but what I mean is that if you maybe also in the class now we have a limited time, so we have just 20 minutes, but try to go through again with what I explained here in class, because again, especially this circuit is not as straightforward as it seems, and try to understand the logic behind. Then if you don't understand, feel free to ask me during the next lecture or during the the lab also.
Yeah, sure. Thanks.
Okay, let's go and continue here.
Oh, I'm sorry. Did you decide anything on the lab already?
Yeah, for the lab, we discussed the very beginning of the course, of the lecture, where will be tomorrow, and I will provide more information in Canvas. And there are some rules that I discussed at the very beginning, but if you maybe we can discuss after the class, then that would be great if you want more information there.
Yes, please. Thank you.
Great. Let's proceed. Last part. So I don't have anything else theoretically to explain. You should know now at this point to know how to design circuit and how to analyze them in theory, in the very theory. The last things I have to teach you is about how to build the circuit in real life. So practically what will be done maybe in the lab mainly. So I want to give you a few hints here. What you will see in the lab is that you will work with one component, which is called CD4007, which contain 3 PMOS and 3 NMOS. However, there are also some components which contain just one MOSFET. For example, this one here that I draw here in the top right side is called 2N700, which is an NMOS, which means that inside of this package, there is only one NMOS, okay? So we have gate, source, and drain. This 3-pin is gate, source, and drain. The package of this transistor here, so inside of this package, there is a transistor. The package of this transistor here is slightly larger than a resistor, so it's quite small. But here I would like I was expecting maybe that someone of you has some question, like why there are only 3 terminals rather than 4. And the reason is that DC MOSFET is mainly used for, okay, first of all, it's very old, but it was used mainly for analog application. And in analog application in the past was very useful to connect the bulk terminal to the source of the MOSFET. And this in some way go in contradiction with what I told you at the very beginning of the last class, where I told you that the PMOS bulk is connected to VDD, and instead the bulk of the NMOS is connected to the ground. It's always like that. Nowadays, it's always like that. But in the past, but this is because today we electronic engineer design mainly design a circuit with MOSFET in integrated circuit, in ASIC, so in microelectronic circuits. In the past, there was not the technology, the photolithography technology for creating microelectronic circuit. Therefore, they use this big component, this one like this one that I show you now, to create MOSFET circuit. So since they have this kind of components, in analog electronic, is actually, you will see later on why, it makes sense to connect the bulk with the source. But this is mainly one thing in analog electronic. And this connection is done inside of this package. That's why you don't see the bulk, because the bulk is actually connected in the source here, and you don't need to connect to anything else.
So theoretically, Luca, this is a constant PMOS then?
No, this is still an NMOS.
Ah, NMOS, okay, yeah.
This is an NMOS.
Yeah.
But there is no the bulk because it's connected to the source.
Yeah.
And again, it might be a little maybe challenging to understand why this is the reason, because I have to explain analog things. But again, I just brought out these things just to show you, just to let you know that there are some package of MOSFET which have 3 rather than 4, okay? And this you should be aware of it. Again, if you have any doubt, then you open the data block, the data sheet of the components, and then you look there. What is the meaning of these three terminal? Usually this one is source, the middle is gate, and this one is the drain. Okay, let's go forward. But again, this is an all component. What you will use this here in this course is called CD4007, which is this one here on the right. This one look like an insect or like a centipede, as you may want to see. The most important part of the centipede, as you know, the insect, is the head, of course. And also for this component here, which we will call it from now on integrated circuit. The head of this integrated circuit is the most important part. And you can see is this part here in blue that I circle here. So this part here gives you the orientation of this component, okay? Once you check where is this part here, then you know what is the pin 1, the terminal 1 of this component. This component has 14 pins, 7 on one side and 7 on the other side, which are practically the leg of this insect. And you can connect to the MOSFET inside this component through this pin here. Inside of this package, there are 3 PMOS and 3 NMOS, okay? So, this one is called integrated circuit because there is more than one electrical component inside. Okay, it's like a circuit. And maybe I should remove the here. Okay, so how do you know what is inside of this integrated circuit? You use Google, and then you write there CD4007, which is the name of this component. But then when you Google it, there will be different items here, because this CD4007 is made by different company. So you also have to know which is the company that fabricated your components. And this one you can understand it by looking about the symbol here, which is the symbol of the manufacturer of the component. In this case, this symbol here is the same of this one, which is Texas Instruments. So whenever you go to Google, you search for the datasheet of the CD4007 from the Texas Instruments, okay? You click there. Usually the data sheet is better when you do the research in internet if you search for a PDF, okay? So you just have the document there. And then you go to the data sheet. Opening the PDF, you get this, and there are many information. The most important information for you is this one here, where you show how many PMOS and NMOS are inside of the CD4007 and how they are connected. Now you can see that in this slide, there are some, you can recognize the PMOS because there is a P, okay, and the NMOS where there is an N. This is the same figure that I found from the datasheet, okay? There are important information here. One important information is that the power supply of this integrated circuit has to be connected all the time to pin 14, which is this one here. And the ground, which here is called VSS, has to be connected to pin 7. If you think about it, this makes sense because look about this PMOS here, for example. You see the bulk is going here, and then it's going to P14. And the bulk of PMOS has to be connected to VDD. That's why pin 14 has to be connected to VDD, okay? So this pin here must be VDD. If you connect to something else, the circuit does not work, okay? And also this pin here must be ground, otherwise the circuit does not work. So if you can see, all the bulk of the NMOS go to the 7. And all the bulk of PMOS go to the 14. Okay. But now the question is, how do I know in my integrated circuit which is the pin 1, pin 2, pin 3, pin 4, and so on? Well, again, as I told you, you have to just check where is the head of this insect here, which is this one here. And then you go to look about the first pin on the left. This one is the pin 1. And then you have pin 2, pin 3, pin 4, pin 5, pin 6, pin 7, pin 8, pin 9, pin 10, pin 11, pin 12, and so on. In this case, we have 14 pin. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So you have to just check this guy, this sign here, this mark here. And then you understand. So this means that the drain of this NMOS here, you can access it or you can connect it if you connect to the pin 5. This source of this NMOS here, you can connect it if you connect a cable to the pin 4 and so on. Okay, I hope this. But it's also important that you see that there are some connections that are made inside of the integrated circuit. For example, the gate of this PMOS and the gate of this NMOS are already connected inside of the integrated circuit. Okay, so you can access to the pin 10, which means that you can access already to both PMOS and NMOS. Okay, so you don't have to do this connection between the gate of this PMOS and the gate of this NMOS because they are already done inside of this integrated circuit. You can only access to this pin 10. I know this can be a little difficult at the very beginning, but I try to explaining as best as I can. Okay, this one is the representation of the MOSFET that you can find in the datasheet. However, it may be more useful for you to do an hybrid representation between this one and this one here, which is this one here. In this way, you can understand better how the MOSFET are connected to the different pin. Okay, so this one should make you in some way easier the life. The dashed line is the bulk of the P, and here the dashed line is the bulk of the NMOS. So maybe when you draw your things in a paper, you can use this one if you wish. Again, P1, P2, P3 are PMOS, and N1, N2, N3 are NMOS. It's very important again, I want to mention again, and this is very important because every year in the lab, as I said before, students come and say the circuit doesn't work and power supply is not connected. The circuit cannot work without power supply, so you must connect pin 14 with the positive terminal of the power supply and the pin 7 to the negative terminal of the power supply. If you do not do that, I mean, don't wonder, I mean, no wonder that doesn't work, right? So, but some of the students still believe that it can work. So then, yeah, so without power supply, circuits cannot work. Okay, so here I want to just show you very briefly a case of study. So I want to show you how to build very fast, so I'm not going into in detail, how to build an inverter by using this integrated circuit. So I want to build an inverter by using this CD4007, which is in the right. And the result is kind of this one here. So of course, pin 14 has to be to VDD, which is this one here. So this one is P1, okay? This one here is P1. Let me draw it. This one is this. And this one here is, oh no, let's say something wrong. This one here, the PMOS is P2, and this NMOS is N2. So N2 here, this MOS NMOS here as the source to ground. So the source of this NMOS go to ground. The drain of this NMOS, which is here, pin 5, has to be connected to the drain of the PMOS. You see here, they're connected together. The source of this P2 has to be connected to VDD. There it is, here. And the bulk you don't need, but the bulk of the PMOS is connected correctly because you connect this pin 14 to VDD. And the bulk of the NMOS is connected correctly because this pin 7 is ground. The gate of the P and the N has to be connected together, but as you can see, this one is done already inside of the integrated circuit, so you don't need to do it. And then the input is applied at the 2 gate, here the P and N. So it means that it's applied here, in this point here. So you have to put the input here. And the output is taken between the drain of the P and the drain of the N, here. The drain of the P, the drain of the N. So I hope it's clear. We're almost done. Okay, so again, in this course from this year, I want to teach you to use Tinkercad for building circuit and drawing circuit on breadboard. And this one will be very useful. So the same circuit I showed before will be realized in Tinkercad like this. One last thing about Tinkercad. I don't go in detail. There is the tutorial in the lab, so look about that. The only thing I can say is this. Unfortunately, in Tinkercad, there is no component for CD4007. So what you have to do is use this other component, which is called 74HC00. It doesn't really matter because we don't use this schematic for simulation or whatever. But the important is that the component we use has still 14 pin, right? So that's why, so when you go to build, and I also wrote in the tutorial, when you go to build this drawing, you have to look for 7400, but we use it as a CD4007. Then we have a power supply, which can be a battery. Here you put a battery, but can be also a power supply, a real power supply. Here we have signal generator for the input. So this, the negative terminal of the signal generator has to be connected to the reference node of the circuit, which we said is the negative terminal of the power supply. The positive terminal of the signal generator go to the input signal, the input of the circuit. The oscilloscope is the same. So the negative terminal of the oscilloscope has to be connected to the negative terminal of the power supply, and the positive terminal of the oscilloscope has to be connected to the output of the circuit. I have one question for you. So this one, I don't have to say anything else, I suppose. Are you familiar with this component here? Do you know what is this? Have you ever seen or touched it? So please let me know because, okay, I have some feedback, thumbs up from Ole. So I hope that you know how it works at breadboard. This is very important. I won't go in detail. And for me, at 3901, I think maybe someone may have some, maybe less familiar. But again, if you are less familiar, please look some video on YouTube or some tutorial about how this breadboard works, because you will work with that tomorrow.
I think we had, I mean, we had it in electrical circuits. Like
Okay.
we had to use one of them. So I think it should be fine. Probably need a few minutes, you know, to kind of like remember how exactly to work it out. But after that, it's fine.
Great, great, great. So, yeah. Okay, so I don't go in detail what is this line here. These are wires, of course. So yeah, you know. Okay, so here I wrote, I would like to show you actually how to use Tinkercad to realize an AND, but if there was time, but it seems there is no time. So it's something that I anyway solved in the preparation for the oblique, and also I think in the lab you're going to build a 2 NOR logic gate. So it's similar to what I've shown here. So So the circuit tomorrow of the lab is to NOR logic gate, neither too difficult. I hope that you don't find any issue. But anyway, I will be there. One last thing before to finish, maybe. Yeah, here. Yeah, because this is important. Okay, I have to draw it here. Here. Okay, very briefly, very fast, one thing. If you remember the NOR logic gate, I just draw the P part, okay? Then the NMOS is down like this. I don't draw the N part. This is the top part of NOR logic gate. The bulk of the top PMOS is connected to VDD. The bulk of this one is connected to VDD here, because all the bulk has to be connected to VDD. It's important that you understand that this MOSFET here cannot be implemented with this MOSFET here. It cannot be, because as you can see, this PMOS here inside of the CD407 has the source that must be connected to the pin 14, which will be VDD. But the source of this PMOS here is connected to the drain of the other PMOS. So this transistor here cannot be used to implement this PMOS here. It cannot be. But you can use this one to implement this, but not the other, okay? This is something I want to point it out, because I think someone of you will do definitely that, but I just warn you. Okay, so I think with the concept that I explained now, I have concluded most of the things. Maybe I run a little in these implementation things, but you will have more experience tomorrow in the lab probably. I will put the time schedule of each group after that you send me, after that I get all the name of the groups. Otherwise I cannot do that. So please send me the name of the groups before 4 p.m. maybe, or maybe 5 or 6, yeah, but not after. So I can divide the group and I will put there the time schedule, okay? I have to decide if you will come all in once or maybe in 2 little slot. But you will know it in the canvas, in the Kune-Joeringer. Yeah.
Luca, should we send you a message if we already hooked up to a group, or do you see it in Canvas? Some of us has already put us in some groups, but should we send you a mail also?
Yes, just please do it, so I have a double check that you have done it. And
okay, that's okay.
Yeah, so let me check in my canvas if I see your, yeah, I see someone did it. If you actually, if you do it just yourself would be also okay, but if you send me just a message would be very nice.
Okay.
Me. Yeah.
Yep.
Okay, so I finish everything with this class about digital circuit. It was 2 entire lecture about digital electronic circuit with MOSFET. I won't probably go in any more detail about this topic here. So this is everything you have to know. We will come back a little once I explain a little analog characteristic of transistor when we go in analog electronics. But at this point, you should be able to know these things I listed. So you know that, I hope that you know that an electronic circuit required to be connected to power supply. You know what are the symbols for the positive and negative power supply on the schematic. You know that digital circuit can be represented by VDD and 0 volt or square wave. Digital circuit are realized by electronic switches, which means transistors. There are 2 types of transistor we are looking at: MOSFET, PMOS, and NMOS. Circuit with PMOS and NMOS are said CMOS because PMOS and NMOS are complementary. And now you should be able, also I give you the knowledge to analyze and design circuit. This is all. And if you have any question, feel free to ask. I have maybe 15, 10 minutes to remain here. And yes, please.
What's the topic of the next lecture?
Okay, from the next lecture, we're going to electric review. So we're going to review directly what you've done in electric circuit theory. So and that is actually the most demanding part from you probably, because I'm expecting that you will remember Norton and Thevenin, parallel series of resistor, parallel series impedance, parallel series inductance, parallel series capacitance, a constitutive equation, which means VL equal LDI divided by dt, which is the derivative of the equation. I think actually that this is probably something that I've been told by the previous students, you will have some challenge, because Jorgen doesn't like to use or maybe go to the derivative things of his equation. But in this course, we will definitely use derivatives, integrals, and just ordinary integrals and derivatives, not surface integrals or whatever, but just normal integrals. We will use the Laplace transform, but this one is something I hope Neon will start to present, and also Fourier transform, Fourier series. So please look at those very well. But for the next lecture, which is tomorrow, actually, I will go through review of this concept of parallel resistance and so on. I don't know if you know actually about transformer, but we need. So I have to provide a few information about transformer. Other things, I might mention something about impedance, AC analysis, DC analysis. So circuit with constant voltage, circuit with variable voltage, phasors. So there are many things that we are going to use, and I know this is the most probably demanding part, but again, we are going to use them all. So this is, as I said at the very beginning, is a difficult course, and if you don't know these basic things that we did from digital technique, that we did until now from the course with MOSFET as a switch, and if you don't know the part of electric Kretzer, I assure you that you won't understand what's going on with amplifier. That for sure you at that point, I suppose, if you feel that this course is maybe you prefer to dedicate your time in mathematics, then do that. One thing. I've known from a past experience, because this is what happened, that students choose. In the sense, this should not happen, but it may happen many times that students choose in the end to focus on electronic or mathematics too. This just to tell you how much difficult will be this course. So this is actually is a pity, because you should be able to do both exam, but in my experience, I've been told from the students that at a certain point they had to choose, because here the amount of work is a lot. But again, I want to emphasize again that these things that we are doing now in this course is the conventional curriculum in any introductory course of electronic. So it's not something special. The difference from your course here in the USN and the other course in all the Europe is that in all the Europe, they don't have the packaging part. And they, mainly the packaging part, and maybe the project is not as important as in your course, because as I said before, the project is 60% of the grade. So then that could be an issue. So if there was not the packaging part, then I would say it would be much easier for you. But unfortunately there is, so we have to cope with that and deal with that. By my side, again, what I can do, I can try to do as much as I can to make it simple. Again, as I told you, in digital technique part, I try to remove the complicated part from transistor. In the oblique, I try to reduce the question, which last year maybe were 30 questions mandatory to solve with all the solution exact. This year there are only 6, but they are random. So I try to make it simple if I can. Any feedback from you is always welcome. If I can simplify in some way, I will try to do it. But anyway, it's a course that demand. So you have to work. Okay, so if any one of you has some question, otherwise we can stop here and then we can continue tomorrow morning.
Luca, question, short. Will you put the PDF for the lecture tomorrow on the Canvas today, so we can
I will try
look
to
at
do
it before time?
You mean that one for the lecture of tomorrow?
Yeah, please. Yeah.
I will try to do it today.
Yeah.
But it might be not that one final, because then I may change something, but I can put it if may help you to see what you have to go through. So
yeah,
I can do that. Yeah, definitely.
Thank you.
Are you going to upload the videos that you're recording now? And I tried to look for the YouTube links, and I couldn't find it. So I'm not sure where you sent it.
Yeah, for the lectures, they are registered by Ole, so he will provide to you, I hope, the information about how we intend to share it. But for the Canvas, then I can very fast show you where it is, so you can then see. Can you see my?
Yeah, I see it. In the meanwhile, Luca, is it possible that I can send you the links to the lectures and you can put it in an announcement? Because I can't make an announcement in the classroom.
I can do it. I can maybe put your maybe. Okay, so here, if you see, there is the part of the Forelesning notator, and